Maybe something to do. I haven't even looked at the weather yet.
Hopefully it's bad here.
Yeah. Do you happen to know GoToMeeting well enough to know how to start recording? That should is recording on your end? That's okay. I'm recording in there.
I do know my resources though. Like,
oh, I think I need to do the other thing is a sound check. The all right, this is a sound check to see if those in hyperspace can hear us. If you can, please chat back that you're able to hear. Thank you very much. I appreciate that. All right. I'll go ahead and close the doors and we'll start up. All right. There we go. Excellent. All right, welcome everyone. Make sure you can see okay. There we go. Cool. Hey, welcome. Please come on in. Perfect. Good timing. And so welcome to all of you who came and to those of you who are joining us via hyperspace. This is part 6 of the propensity scores and related methods, where we're looking to extend the ideas we've developed in parts 1 through 5 into 3 groups. Part of the interest in this is, as Christiane can share, we have interest in doing this ourselves in a study where we're going to be comparing metformin monotherapy to sulfonylurea monotherapy to TZD monotherapy. That's one setting where it's within a context where all 3 exposures are of interest. And so it'd be nice to be able to define a population where people could be on any one of the 3. We're also, another context where 3 groups is nice is, say you have 1 exposure of interest and 2 possible data sources for control groups. That's actually a great 3-group setting, especially if those 2 control groups have different concerns about them in terms of unobservable bias. That's a nice context to have 3 groups. And nothing we're going to talk about can't extend further beyond 3 groups. But this initial intellectual exercise of taking what we know about 2 groups and extending it to 3 groups ends up being really useful. Throughout, I'm going to be pinging back to things that we've learned about the 2-group comparisons and refreshing our memory and getting us to think about it a little bit more deeply in order to extend it to the 3 groups. I'm going to set up with a little bit of causal inference terminology that we've touched upon before, but it ends up being very helpful to think about that a little bit more carefully, especially when it comes to the weighting. And then we're going to look at extending 2-group techniques to 3 groups, some theoretical and technical considerations. And then next time we're going to, God willing, be doing this in the example of our particular interest. And as always, we keep this informal. Discussions and questions are welcome throughout. So Jim Gaffigan has one of my favorite quotes. He says, there's 2 philosophies when it comes to getting young children to sleep. There's sleep training, which basically involves putting kids to bed and listening to them scream all night. Or there's attachment parenting, which essentially involves lying down with your kids, cuddling them, and then listening to them scream all night. I'm in the
Dumbo. Dumbo.
I've been in I'm in that latter camp, and so I definitely caught my eye this morning when the New York Times had this headline that parents shouldn't feel guilty about training babies to sleep. It was a 3-arm randomized controlled trial published this week in the journal Pediatrics. It had a small n, so I'm not going to, although the headline has quite big claims, I'm going to hedge that with saying 43 children here, aged 6 to 16 months. It was a 3-arm trial. It was a graduated extinction arm, which lets children cry for predetermined brief segments of time. There's bedtime fading, which delays bedtime in 15-minute increments until the kids are just exhausted enough to fall asleep. And then there's the control, which was just sleep education. It compared between the 3 arms, time to fall asleep, mean cortisol levels in mom and in baby, the parent-child attachment at 12 months, at least at 12 months. They could not discover the development of any sociopaths due to sleep therapies. And the reason why I bring this up is the randomization in this trial facilitates estimating the average treatment effect between any 2 of the 3 arms. That if we are interested in the mean effect of graduated extinction versus control, or graduated extinction versus bedtime fading, we can, within the population of infants as defined by whatever their sampling method is, however they went about getting these 43 infants, that defines the population of interest. And once they have that population of interest defined, they're interested in the average effect, average comparative effect of these treatments in that population. Now, randomization is nice because it lets us actually estimate that thing. In general, when we move to observational studies, that really can be a hard thing to estimate. It really requires that the positivity assumption be true and really true. That is, that assumption that whatever a person's set of covariates, there's some chance that they could have received any of the exposures. Often in an observational data set, that's not true unless you have very careful inclusion criteria that force it to make that the case. And the data set needs to be sufficiently plentiful in all exposures. So even if in theory that positivity assumption is true, it needs to be true in fact of the data as well. There has to be real people with really spanning that shared covariate space. Now, many of the methods that we look at are not trying to estimate the ATE, though some are, and thinking about when they are and when they aren't is important to thinking about how to extend these things to 3 groups. Now let's remember the 2-group propensity score. Using the observed data, we estimate the probability of being exposed versus not being exposed, or being treated versus being control, given the person's covariates, and that is our estimated propensity score, which in the standard literature we write as E of X. The exposures predicted by covariates yielding this predicted probability of exposure, and this can be done using any number of fancy methods, a random forest, some variation of CART, but most often we just use a logistic regression. And it's nice because we really trust logistic regression. We know a lot about it, we're fairly comfortable with it. That's an idea that we're going to circle back to when we think about getting to 3 groups. So what do we do with the propensity score? What do we do with this estimated quantity? Well, one, we can match on it. We can weight by it. We can stratify by it, which is really an older approach. The downside to stratifying by it is that we now have to do some sort of stratified analysis. And it only partially adjusts for confounding in comparison to these other approaches. we can adjust by it. That is, we can use the propensity score as a covariate. There are those out there still advocating for this approach. At some point, I want to give a talk in depth as to why I argue this should not be done. It doesn't mean that it's never valid. That's not what I'm saying. I'm not saying that it's completely invalid. I'm saying that given this list of choices, I would be surprised to find a scenario where there's a possible choice. Something I have to remind people of is an option on the table is do nothing with it. It's possible that the data set's just not rich enough to really do anything useful with a propensity score, that maybe the best you can do is just do direct covariate adjustment on your top 3 covariates. Just pick the 3 covariates that matter the most, and that's all your sample size can handle. And last I've added in from previous slides is to do doubly robust estimation, which can be combining matching or weighting with covariate adjustment, which also will make a nice future talk. So what can we estimate? When matching, it's rare that we would ever be estimating the ATE. Because when we match, we almost whenever we're matching, we're doing something to shift the population set of covariates. If you imagine taking ignoring group and just looking at the distributions of all your covariates in your cohort that you're pre-matching cohort, your cohort that you're getting ready to match. And then you do some sort of matching because there's an abundance of exposed people in this one particular region and a paucity of exposed people in some other region. If there wasn't some kind of imbalance in the covariates, you just analyze the cohort as is. And so you're motivated to do the matching. Hey, Lena, you're motivated to do the matching because there's some pre-existing imbalance. And the matching gets rid of that imbalance. That's what you want to happen. That's why you're doing the matching. That's also changing the population of interest. The population of interest is now the population that has this distribution of covariates that got formed by the matching. Now we formalize that depending on how we do the matching. If it's the case where all of the treated subjects or almost all of the treated subjects can get matched to. Say we do a simple 1-to-1 matching or simple 1-to-4 matching, and all of our treated subjects can get sufficient matches to them. That we now think of that population as being the average treatment effect, or we think of this estimating the average treatment effect among the treated. That the covariate distribution that we morphed to was that of the treated subjects. And so if we looked at, pre-matching, what does the covariate distribution of treated people look like? And then post-matching, what does the covariate distribution of that whole cohort look like, that whole matched cohort? It'll look like the distribution of the treated people. And so we've morphed our cohort into something that looks like the treated people pre-matching. Now the ATC, the average treatment effect among the controls, is just semantics. It's whether you're calling that group that you're morphing to the treated group or the control group. And last time we introduced this idea of the average treatment effect among the matchables, or among the richly matchables. Lori and I are working on some good term to explain this, as it's a fairly new idea. But it's really thinking about what we actually do in matching. That when we usually match, we know that this positivity assumption doesn't really hold in most cohorts that we have. But we do something smart, like we use a caliper. And that caliper says if people can't get a match on propensity score within a certain range, they don't make it into the cohort. And so we're essentially pruning our data set. It's almost like a hidden exclusion criteria that goes into the matching process. And sometimes people get dropped because there's an overabundance of them. And so there's just a whole bunch of people, but this small group of people can only match so many of them, and so the excess will get dropped. But the population that we end up with is essentially the population that the matching ends up forming. And we don't have a super formalized name for that in the literature yet, but we can think about it as the average treatment effect among this matchable population or this richly matchable population. Another way to think about that is imagine within a certain region of the covariate space, there's a whole bunch of people in one group and just a few people in the other group. Those whole bunch of people are providing too much, being given too much weight in shifting the covariate distribution. So the matching gets rid of all but just a few of them. And so essentially the impact of that abundance of people gets shrunken down. Now suppose in a different region of space where there's an abundance of treated people, but there's only a few available controls. The same thing's going to happen, but in this time to the treated people. It's going to be the treated people who the excess gets discarded and the controls will get the one-to-one matching. And so that's the morphing of the distribution that the ATM is doing. And of course, those regions with non-positivity just get dropped completely. If there's no treated or no controls within a certain region, they just get dropped. Weighting can give us any of those things as well. Via weighting, we can get the ATM versus the Lee and Green style weighting, which we'll revisit. We can get the ATT or the ATC versus via stabilized weights. And under friendly scenarios, we can try to estimate the ATE. That if we have a pretty friendly data set or pretty cleverly created inclusion criteria, we can try to estimate the ATE via weights. And we'll revisit how we go about doing that and see how it extends. Stratification, as I mentioned, it really depends what that quantity is trying to answer and whether or not that quantity even in the stratified analysis even collapses to any of these things that we think it would. If we adjust by it, if we adjust by the propensity score, that gives us a beta. We essentially are fitting some sort of model with a propensity score in it. And our exposure variable gives us a beta. Likewise, if we do nothing with it, if we just do direct covariate adjustment, we also get a beta. Now, between the two scenarios, I actually find 5 a little bit more friendly in that, at least in this scenario, we could try to get at an AT anything, really, ATE, ATT, any sort of population that we posited a distribution of covariates on. We could try to, we could get what our model says the average treatment effect is by projecting onto that space, essentially seeing how our model would project predicted values for the pseudo cohort and then calculate an average treatment effect within that pseudo cohort. And finally, a doubly robust estimation. The answer is, again, it depends. There isn't just one way of doing doubly robust estimation. Some can yield the ATE, some do not. But the ATT is often the goal there, and there are methods that can give that. Now, the key part of going through that is really just understanding the population. That to a certain extent, these careful definitions from one perspective can be thought about much ado about nothing. That what really matters is understanding the population that you're predicting. To put it another way, if the population, if the sample itself is collected in some sort of haphazard or very unique sort of way, then defining a population, defining the distribution of covariates based on that population isn't super generalizable to begin with. And so sweating how well our particular method is mapping back to the distribution of those kind of haphazardly gathered covariate distributions isn't something I see a lot of reason of to sweat over. It is useful, however, in getting to be reminded of two things. One, we should be thinking about the actual distribution of covariates in the population that we're predicting. And that's something that goes in the paper. That's our good table of characteristics. A good table of patient characteristics can go a long way into helping us understand the population that we're talking about. Two, it's useful in thinking carefully about how these different approaches will give us estimable quantities. That said, it can make a big difference in the actual effect sizes you report. Think about it. Does anyone remember back to Obama versus Romney and the unskewing of polls that went on? This was the thing that there were sites out there that were saying all these polls saying Obama's going to win are totally wrong because they're just based on the weighting that these particular polling sites use. These polling sites, call up 10,000 people and 100 people answer. And so they have to do something with that little sample of people answering. They know they have enormous response bias in there. They have to do some sort of adjustment. They do that via weighting. They take information they can get about that person and they upweight or downweight the people that they actually got to respond to fit some sort of population that this population of likely voters that they get. And so the argument is, in that context, you can make these polls say anything you want, and that's true. You can make these, depending on sort of what population you're averaging to, what population you're weighting to, you can make that polling data say anything you want, and we're going to get to see that plenty over the next 6 months or so. However, 3 months, 4 or 5 months till the can't come too soon. So the key really is in describing this population well. So we're going to be in a context more like this one, that there's some sort of retrospective study that you could imagine, looking in this case volatile anesthetic choice on hospital length of stay, and this isn't very readable. Oh, actually, it's not terrible from where you're sitting. But the idea is you have your description of your cohort. In this case, it's a true 1-to-1-to-1 propensity score matching. Nice even sample sizes there. In this particular case, they didn't match as nicely as I think they could have. I think they could have pushed the balance a little bit harder in terms of the quality of the matches they get. But this gives us an idea of who it is that they're talking about, which is what we're after.
Can I ask? Oh, right.
Yeah.
Your comment, is it just because of your experience with matching that you think they could push the boundaries, or is there something that we would know? I mean, because just on initial glance, I'm like, a lot of these numbers are pretty close. So what makes you make that comment?
It's a good point. Within, and it depends a little bit on context that I'm not knowledgeable enough in this area to have, so they might have made the right trade-off. But there's some of these here that we're showing just a little bit of imbalance, not tremendous. Here, like in here in the interoperative opioids, those percentages are a little down. Now, I don't know if this has a big impact on length of stay. If it doesn't, if this isn't going to have a big impact on length of stay, then yeah, I don't want to lose much of my sample size trying to balance it.
But given that the sample size is already pretty large, they could give up a few people to make, if it were important, they've got a sufficient sample size to probably improve the matching.
Yes, possibly. Okay. And that was my intuition.
Okay.
But that said, I didn't get to play with this particular data set. But it does bring up a nice point that they're kind of tying back to how rich is the data set itself, because there are data sets where people will try matching and find out it's just not working no matter how much. They have to trim it a ridiculous amount in order to get a well-balanced cohort, and that can just be a limitation of the data itself. There's times when there just isn't good overlap or isn't a lot of subjects to work with. So the three-group matching creates some interesting problems. To solve it in the purest sense, it can be computationally intensive. I'm not sure what I mean by inhibitive in that slide, but possibly even prohibitive to try to do it, depending on your objective in the sample size. But you can leverage two-group matching techniques to do it, which is often done. So let's remember our two-group matching variations. We have the greedy matching, which is you can greedy match on the propensity score. You keep the propensity score often on the log odd scale in order to get better differentiation in the tails. And You take the first exposed person, get the best match you can for them, pull those two people out, take the next exposed person, get the best match you can for that person, and pull them out. Some downsides to the greedy matching is the order you grab those subjects will give you a different set of matching. Each different ordering might give you a different set of matching, so it's not completely deterministic. You can also end up with poor matches towards the end. If it's not a super rich cohort, then after you're giving everybody their first pick, essentially, as they're going along, when you get towards the end, there can just be some pretty bad matches available. So one solution to that, which if the data set's not too large, is optimal matching. And we've even performed an optimal matching on a scale of like 1.2 million by doing some clever stratification, is to do a process that essentially looks for the set of matches that will give us the smallest average distance between pairs. And you can imagine that's a fairly intensive thing to do, because if you think of every n choose n over 2 set of possible matches that you could get at least, and that's just an even dividing. It's often, the scale is often bigger than that. Just the enormous of things to look at. But there are special algorithms that can find that optimal solution. We talked already about having calipers in there to automate a pruning process that can be done. We can match on things other than propensity score, such as prognostic score or risk score, or on a reweighted Mahalanobis distance. For those things, there's chameleons, which are a version of a caliper that lets us automate that pruning process. There's coarsened exact matching, which you can imagine as sort of a multivariate histogram, creating a whole bunch of little bins in which you can match exactly within those bins. And then there's other variations. There's like an 8-to-1 exact propensity score matching and numerous others. We're going to focus, I'm going to have you just kind of keep the idea to keep in your mind at the moment is pretty much just think about the greedy matching. Just because the computational complexities are going to be big enough, hard enough already. We are going to set up some frameworks that do let us leverage optimal matching and some of these other options, but it can be easiest to think just about the greedy. So here's the issue of pairs versus triplets. So in pair matching, we just have matching our red subjects to our yellow subjects here, and we're just creating all these different pairs in some sort of sensible way like that we talked about. The catch in the triplet matching is, in the purest sense, we're really matching a red to a yellow to an orange back to a red, where all three of those distances are of interest. That's a hard thing to do. That's a hard thing to do, because once we've formed, to actually go through and search the space of all the possible triplets is just a computationally intensive thing to do. So we can leverage getting triplets from pairs. One way to do this is to pick a group and form pair matches from each other, from each of the other groups independently to that group. In this case, pick red as the master group and match to the yellows and match to the oranges, and just forget about that yellow to orange distance. That lets us use 2 pair matchings in order to form a triplet. Now this is very natural when having 2 control groups or having one exposure that is clearly our reference exposure that we want to map everything to that particular exposure. Now using a caliper is important, but it creates a wrinkle. What happens if our red subjects disappear in one of those sets of matching? Now the quick solution is just to drop any incomplete triplets. If they weren't able to match on one or more of our desired cases, just go ahead and drop them. Now optionally, we can redo the matching after dropping subjects from just the master group. So imagine doing this, dropping all the master subjects that end up getting excluded in this process, and then redoing the matching. The reason to do that is maybe there's some really good orange subjects that got wasted by getting thrown out in this dropping step here. And so by keeping all of the orange and yellow subjects in, pruning just the reds and then redoing the matching, you have a chance of getting a slightly better match there. Now you can do this process manually using any of the friendly pair matching packages such as OptMatch, NBP matching, using the prevent option, match it, etc. The R package TryMatch works to ease some of the manual burden that you have to do. There is a concern with this process that looks like this. If we pick red as the master and then match, take its best match to a yellow and then its best match to an orange, we might have a scenario like this, where this orange is really the better match for red. It's a little bit shorter than this orange over here. But if you think about what's going on with that third distance that we're ignoring, that third distance is radically better if we paid a small price for the red to orange match. We would get a radically better orange to yellow match there. And we're not getting that because we're ignoring that distance. One solution is to match the first and second groups and then match the third group to a pseudo cohort formed by midpoints, which is just taking the average of the covariates of the initial matchings made. So the red gets to match to yellow. We then create a pseudo cohort of midpoints, and the orange is going to match to those midpoints. And so in this special case that we made up here, we would now be willing to give up on this better match to orange because yellow would have a little bit of influence on the proximity to what we're matching to, and that matching to that midpoint would have us prefer this point. And I give credit to my programmer Cole for turning me on to that solution within the randomized 3-arm trial setting.
But now it depends on which groups you match first, right? To do the.
It does still depend on which groups match first. Exactly. That ordering still has impact. And really, in the pair matching settings, there's no way to avoid that. Any other questions about matching before we pivot to weighting? So the two-group ATE weighting looked like this. The ATE, or unstabilized weights, created a pseudo cohort by weighting everybody in the cohort by 1 over E star of X, which we define as the propensity score for the exposure actually received by that particular subject. So two subjects can have the same E of X, the same propensity score, but we're interested in the propensity score for what they actually received. So in a two-group case, this is either going to be 1 over E of X if that's the propensity of getting what they actually got, or it's going to be 1 over 1 minus E of X if they're in the other group. If they're in that other group. I want to make sure that thinks for a second. I think I'm getting enough nods there, but that's okay. So think about extending this to the 3-group case. We have this idea of we're just weighting everybody by 1 over E star of X. The ATE, or unstabilized weights, in the 3-group case create a pseudo cohort by weighting the whole cohort by 1 over E star of X, where E star of X is still just the probability of receiving the exposure actually received given their particular covariate values. It's the exact same thing, that there's nothing special when we extend to 3 groups. The only question is, how do we get E star of X? How do we get their propensity score for the probability of receiving the treatment that they actually got? Option 1 is to fit a multinomial model. This isn't a terrible thing to do, but honestly scares most people away So most people get to that step and they say, I've never fit a multinomial model. I'm not sure how well I trust them. There's certainly nuances in these models that I should be worried about and don't know to be worried about, and they stop there and they go and do something different. Those are all fair concerns, and because of that, I wanted to mention option 2, which is to simply fit 3 logistic models. Imagine fitting for any group I, just fitting a logistic model for in group I versus not in group I on the whole cohort. Now that's going to give you a bunch of probabilities for people, all the people we lump together as not in group I, but we don't care about that, right? We're not going to use those. We're only going to use, for those people who are in group I, we're just going to use the probabilities, those predicted probabilities that we get for being in group I versus not in group I. And we're going to use those propensity scores as our weights. Just do 1 over those as the weights. Now remember the goal of the ATE, to remember why that's going to really see why that's going to work. The goal of the ATE is to morph the covariate distribution of each of the 3 groups so that it matches the whole cohort mushed together. So if you think of the covariate distribution of the whole cohort mushed together, we need to take then each of the 3 groups and morph their covariate distribution to match that global covariate distribution. That's what these propensity scores are going to do. For the people in group I versus not in group I, it's going to take the people in group I, and just like it would in the 2-group case, if we only had 2 exposures, it's going to morph that particular group to fit the group on a whole. It's essentially, if you think of what happens in just the 2-group case. In the 2-group case, it takes group 1s and morphs them to look like the whole cohort, and then it takes group 2s and morphs them to look like the whole cohort. And so these weights are going to do exactly what we want for the ATE.
So what if the not in group I is composed of 2 different groups? Based on our example. So we have 2 different groups that are composing not in group I. And what if they are extreme values in them, that they are just fundamentally 2 different groups that now you're asking your model to create a group that looks like the average of these 2 extreme groups?
Nice. And so for those in hyperspace, repeating what the case Christiane said, is imagine that these not in group I, the 2 groups in not in group I are just very different, are covering very different covariate spaces. And the answer to that is that's a setting we're trying to get the ATE is a wrong thing to do. Because the ATE really needs that assumption of positivity, that no matter what somebody's covariate values, it makes sense for them to have received any of the 3 treatments. Even if the probabilities differ, those probabilities have to be non-zero. And so that's a great case where we look at that and go, oh wow, that's a really uninteresting quantity, because the only way to get that quantity would be to do an unethical randomized study. So in a setting like that, maybe we'll say, well, what about ATT weighting? Maybe it's not the case that we can that the ATE weights are of very much interest. What about the ATT weighting? Well, the ATT, or what's sometimes referred to as the stabilized weights, we create a pseudo cohort by weighting the whole cohort by E of x over E star of x. So that denominator is the same. The denominator is still the probability of getting the treatment that they actually got. The numerator is now fixed to 1 group of interest. In this group, we'll just call it generically the treated group. So the numerator is always what is the propensity score for treatment given that set of covariates. Now in the 2-group case, that means depending on what group someone's in, their weight is either going to be 1, it's just going to be the propensity score divided by the propensity score, or 1, if they're in the treated group, or if they're not in the treated group, it's going to be the propensity score divided by 1 minus the propensity score, which for them is the probability of not being in the treated group, or the probability of getting what they actually got. Now let's think about extending this to 3 groups. The ATT or stabilized weights create a pseudo cohort by weighting the whole cohort by E sub t divided by E star of x for a given treated cohort t. It's essentially the same thing. It's still pick one of the 3 groups, fix that propensity score. That goes in the numerator. The probability of being in that particular group for any set of covariates is what goes into the numerator. And then the probability of getting what you got goes in the denominator, and that's the weight for each person. Again, the question becomes how to fit this. Option 1, fit a multinomial regression model. If we're comfortable fitting that model, that gives us, for any set of covariates, all 3 sets of probabilities. You have the probability of being in group 1, the probability of being in group 2, and the probability of being in group 3 for any given set of covariates. But again, not totally comfortable with the multinomial model. We can get here by fitting 2 logistic models. And the trick here is not to fit it on the whole cohort, but fit it on just 2 groups at one time. So imagine fitting 2 logistic models where E star of x for group I comes from a logistic model of in group I versus that treated group. Now, again, we have to remember what the goal of the ATT weighting is. The goal of the ATT weighting is to morph our covariate space so it looks like that of the treated subjects. The weights for the treated subjects are easy. They all get a weight of 1 because they're already morphed. The treated subjects already have the covariate distribution we want. We only have to change the other 2. How do we change the other 2? Well, we can do it just like we would do in the pairwise case. We can pairwise weight each of those other 2 groups. And what matters is just getting their distributions, their covariate distributions, to have that of the treated group. So there's no reason why we have to do that in one big model. We can do those separately, just like we would in 2 pairwise cases. Is there any question about the ATT weighting before we move on? So now we'll move to the trickiest case, but for me the most fun, because both the ATE weights and potentially the ATT weights can have the same trouble of there can be regions of the covariate space that are non-positive or nearly non-positive. That is, that there can, in the ATE weights, in these ATE weights, if there's any region of the covariate space that just is dominated by one treatment, then we're sunk. Estimating the ATE becomes really hard, and the consequences when we try to do it, we see these massive weights for some subjects. Like that one metformin subject, or a better case would be that one person who got put on a TZD even though they had an A1C of 11. That person now gets a weight of 1,000 because they're trying to make up for all those people who don't get TZDs with big A1Cs. Yeah.
For the 3 groups, when you do the option 2, or you fit 3 logistic models, under the ATE, people that's not 3 treatment groups, not ABC, in group I, A, versus not in group I, which means B and C.
Exactly.
However, under the ATT, you're saying you pick a group, and then it would be versus the 3 models for the option.
Oh, and it's just 2 models for here. In this case, we only have to fit 2 models.
So you can say in group A versus the treated group.
Yeah, or let's suppose we made in your example of group A, B, C. When we do the ATE weights, we'd fit. To get the weights for A, we fit A versus B or C. To get the weights for B, we fit B versus A or C, and so on. For the ATT, we pick one of the groups as being the group we're going to morph to. So let's say it's A. So let's call A our quote treated group. Then we don't need to fit a model for A to get their weights because they all just get a weight of 1. But now we need weights for B. To get the weights for B, we just need a model of B to A. So B versus A gives us our weights for B, and our weights for C come from just fitting C versus A. Because both of those logistic models, when we do the weights, as we've described, will just morph the covariate distribution to A. Okay. Nice. So so now comes the trickiest case, and the last case that we'll look at today, which is the ATM weighting, these matching weights. Here in the two-group case, we created a pseudo cohort by weighting the whole cohort by the minimum of being in group 1 or group 2, the propensity score, 1 minus the propensity score, and same denominator, always the same denominator, divided by getting the probability of the treatment actually got. What this does is this picks the group that we're stabilizing to, not as just group 1 all the time, but whatever group based on the covariate distribution happens to be the localized smaller group. So if we're in a region of the covariate space where there's only a few people in group 1, well, if we were doing pair matching, all those extra group 2 people would essentially be getting dropped. Or if we're going to do weighting, we're essentially going to downweight all of them to compensate for the fact that there's only a few group 1 people. Then if we move to a different region of covariate space where there's an abundance of group 1 people, those group 1 people are now the ones that need to get downweighted, and it's the group 1 people, it's the group 2 people who would all get matched or all get a weight of 1. That's essentially what this is doing. If within any region of the covariate space, the treatment that the people are at, those who actually got the treatment that was the least likely, they're just going to get a weight of 1 because it's going to be the minimum of the propensity score and 1 minus the propensity score. And if they're in the minimum, if they're that minimum exposure, then they're going to get a weight of 1. If they're instead in the majority exposure, it's going to be that smaller probability divided by that bigger probability, or it's going to be some weight less than 1. And so a nice feature of these ATM weights is people are always getting weighted either 1 or some value between 0 and 1. And that ends up doing a nice job in the cases where we have those weird regions where one group is really dominating and the other group is extremely rare. When doing either the ATE weights or the ATT weights, we have to risk upweighting that unusual person an enormous amount to compensate for that, to try to get this idea of an ATT weight or an ATE weight, to try to get to that population. Here we say that population is just too hard to estimate. Let's estimate the ATM population, and that we can do quite well. And that's a population we can really estimate well, and we move to that. Now, how do we extend that to 3 groups? We extend that by looking at the minimum of all 3 probabilities divided by the probability of getting what they actually got, and this is our pseudo cohort weighting. I don't have any tricks for this. At least I haven't come up with any yet. And I haven't, to my knowledge, this hasn't been written about. And so there's some open questions here to be answered. But if we are willing to fit that multinomial distribution, this isn't too bad to do, that we would be able to do this. There can be some argument of exactly which variance estimate to use when doing this, but I'll leave that as a discussion for another day. The final thought that I want to share is the proof of the pudding is always in the table 1. that the question kind of remains like, did our approach work? Like we've in presenting this, we're presenting a dozen different approaches. There are pros and cons to each approach, and whether or not approach makes sense depends on the data itself. For example, if you have a data set with say group 3 is enormous. So group 3 is just this massive control group, and it dominates group 1 and group 2. Then in that case, if you picked group 1 as your treated group or group 2 as your treated group, your concerns about extreme weights, at least with regards to group 3, are not going to be there, because group 3 can morph down easily. Whenever you have an abundance of subjects, it's always easier to morph down a covariate distribution to get what you want than to stretch it out. Like if you have these couple 90-year-olds that you have to give a lot of weight to pull the mean of the age up, that's hard. That's a hard thing to do well and reliably. But if you have an abundance of 90-year-olds that you just need to downweight in order to get the mean age down, that's very doable. It's much easier to downweight subjects. And so the relative prevalences of the actual number of people you have in your cohort is important. But whether or not something's working, whether it's a matching or a weighting, my recommendation is always go to the table 1. Go to those figures of standardized differences, because they're going to be the things that really show us whether or not we've achieved good balance on the covariates that we think matter. Cool. Nice. Thank you. Any final questions before we break? All right. Thank you, everyone. Yes.
We put the course from
Oh yes, in fact, yeah, and let me email that to you right away. Thank you for putting that. Yeah, I haven't posted the official version, but let me send you an unofficial version right away.
You're going to approach.
Thanks a lot. It was really helpful.
Oh, thank you.
Vanderbilt or from the street?
I'm probably coming from Vanderbilt, like
Okay.
behind. I'm in.
Okay. Okay. Cool.
And thank you all in hyperspace.